Hey there, Seahawks, it's Miss Adams, and in this video we're going to talk about binomial and geometric probability models. Alright, so these models fall under something called Bernoulli trials. A Bernoulli trial is if we have two possible outcomes, only a success and a failure. The probability of success, P, is constant, and the trials are independent. One way to check for independence is to use the 10% condition, so this works as long as the sample is smaller than 10% of the population. Binomial versus geometric random variables. So a binomial, the definition is we count the number of successes in a fixed number of trials of Bernoulli experiments. The notation is binom and then n and p, or just capital B and then n and p, where n is the number of trials and p is the probability of success. The mean is n times p. The standard deviation is the square root of n times p times 1 minus p. And then the probability model, you can find the probability of the random variable x equaling a number by using combinations and multiplying the probability of success and the probability of failure raised to different exponents. This is all on your reference sheet. So on the front of your reference sheet, there's a section that says probability distributions, and then it has binomial and geometric, and it has the mean, standard deviation, and the other formula to calculate a probability. For geometric, it counts the number of trials until the first success is achieved in repeated trials of Bernoulli experiments. The notation is geom and then just the probability, where P is the probability of success, or capital G and then the probability. The mean is 1 over P. The standard deviation is the square root of 1 minus P divided by P. And to find the probability, it's the probability of success times the probability of failure raised to the x minus 1 power. All right, computer chips have a 25% chance of being defective. Create the probability distribution of x if x is the number of defective chips in a sample of 3. What is the probability of having 2 or more defective chips? All right, so underline some important information here. So I'm going to draw a tree diagram. So there's a 25% chance that a chip is defective. We're doing a sample of 3, so we're going to branch this off 3 times. I'm going to multiply across. Okay, so here's all the different combinations I can make. And when I multiply these probabilities across, I get the following. All right, so the probability that x equals 0 of having 2 or more defective chips, so that there's 0 defective chips, is 0.42188, which means all of them are not defective. The probability of 1 defective chip, so I'm going to count up all the ones where there's just 1 defective in the group. The probability where there's 2 defective chips, and then where they're all defective. Okay, and then what is the probability of having 2 or more defective chips? So I can add those. Sorry about that. I can add these two sections up to get 2 or more. Okay. It is known that only 15% of the population is left-handed. Create a probability distribution for the number of left-handed people in a sample of 3. All right, so first we're going to check, is the problem a binomial or geometric? So in order to be binomial or geometric, I have to have a set number of trials. It has to be independent. The probability has to stay the same. So this is a binomial because they said a sample of 3, so I have a set number of trials. And my probability is 0.15. All right, so it is binomial. The probability of x equaling a number in the combination format, it's n over x, so the combination of n choose x. The probability of success raised to the x power times 1 minus the probability of success raised to the n minus x power. All right, so for 0 successes, it'd be 3 choose 0, probability of success to the 0 power, probability of failure to the 3rd power. Okay, and I got the 0.85 by doing 1 minus 0.15. All right, so the probability of failure would be 100% minus 15%, the probability of success. All right, that gives me this value, and I'm going to repeat this for 1 success, and 2 successes, and 3 successes. And so I can get that probability model there. All right, so would you want to do this, what we did above, if we had a sample size of 50 or 100? No, probably not. All right, so we have different calculator functions that we can use. If it is equal to a number, then we're using a PDF. Okay, so if I'm solving a probability where it equals exactly this number, it is precise. So I think of precise, exact, as my P for PDF, all right, which is probability density function. So there's a binomial PDF and a geometric PDF, just depending on which type of function you're working with. If it's less than or equal to, then it is a CDF function, cumulative density function. In other words, I'm combining. It could happen at 5 or 4 or 3 or 2 or 1 or 0. So I'm combining all of those possibilities together. All right. So that's a geometric CDF. Your calculator automatically does the less than or equal to. And the TI-84s don't really have an option to do greater than or greater than or equal to. You have to do 1 minus for the greater thans. PDF, again, stands for probability distribution function. It gives an individual outcomes probability. CDF is cumulative distribution function. It adds up all the probabilities equal to and below. And both are under distributions, which you're going to do second vars on your calculator to find those. All right, geometric or binomial. So you do need to be able to determine if the model is binomial or is it geometric. So people with O negative blood are called universal donors because O negative blood can be given to anyone else, regardless of the recipient's blood type. Only about 6% of people have O negative blood. If donors line up at random for a blood drive, how many do you expect to examine before you find someone who has O negative blood? All right, so this would be how many until your first success, so that would be geometric. I don't know how many total trials I have. All right, the next one, suppose 20 donors come to the blood drive. What is the probability that there are 2 or 3 universal donors? All right, so this time I have a set number of trials, 20, so this one would be binomial. All right, again with the O negative blood, if donors line up at random for a blood drive, how many do you expect to examine before you find someone with O negative blood? And what is the probability that our first O negative donor found is one of the first 4 people in line? All right, so I'm checking. So the conditions I'm going to check for a geometric, because again, this is until the first success, is going to be BIF. So binary, success or failure, check. Independent, the sample is less than 10% of the population. All right, we can assume that. Also, we can assume that one donor is independent of the next donor. Until our first success is what we're going to keep going until the first success. And then we have a set probability. The probability stays the same at 6%. All right. So this is a geometric distribution with a probability of 0.06. My expected value, which is that first question that they're asking, is the mean. So the mean is the expected value. You can look on your reference sheet to find that formula. So the mean for a geometric distribution is 1 over p, so it's 1 over 0.06, which is 16.667. All right. So I would expect it to take about 16 or 17 people until I found my first O negative blood person in that random blood drive. All right, then the other question, what is the probability that the first O negative donor found is one of the first 4 people in line? So the probability that it's 4 or less, like that the first one happens in the 4 or less people. So this is a geometric CDF because I'm combining, it could be the first person, the second person, the third person, or the fourth person. P is the probability of success, 0.06, X is 4, and I get 0.06 21925. All right, so in my calculator, I'm going to second bars, which is distributions. I'm going to find geometric CDF, and I'm going to put in P and X and get my answer. All right, suppose 20 donors come to the blood drive. Recall that 6% of the people are universal donors. What is the mean and standard deviation of the number of universal donors among them? And then what is the probability that there are 2 or 3 universal donors? So this is a binomial. So our conditions are going to be bins. So B, binary, I, independent, N, set number of trials, and S, set probability. So binary, success or failure. Independent, the 10% condition is met here. Number of trials, we have a set number of trials where N is 20, and we have a set probability of 6%. All right, so this is binomial, where N is 20, and the probability of success is 0.06. The first one is asking for the mean and the standard deviation, so the expected value. E of X, or mu of X, is N times P. So 20 times 0.06 would give me 1.2. And the standard deviation is the square root of N times P times 1 minus P, which when I plug that all in, I get 1.06. Right, and those would be 1.2 donors and 1.06 donors. All right, the probability that X equals 2 or 3, I'd have to find the probability that X equals 2 and the probability of X equals 3 and add them together. Because this is not, I am combining, but it's not all the rest of them. I'm going to do them separately and then add them together. So I'm going to do a PDF for precise for 2 and a PDF for precise for 3. All right, so a binomial PDF where N is 20, P is 0.06, and X is 2. And then another binomial PDF where N is 20, P is 0.06, and X is 3. And I'm going to get those answers, and I'm going to add them together to find my probability of 2 or 3 universal donors is 31.06%. All right, John is taking archery. He has a 30% chance of hitting the target each time he shoots. He shoots 8 times. All right, so this is binomial, okay, because he's shooting 8 times, there's a set number of trials. So I'm going to check the binomial conditions. Binary, hit or miss. Independent, we're going to assume independence. N equals 8, my sample size. And my set probability is 0.30, 30%. What is the probability that he hits the target 4 times? So this is binomial again. So this would be a PDF because it's probability X equals. All right, so binomial PDF, N is 8, P is 0.3, and X is 4. We get 0.1361. What is the probability that he hits the target 2 times or less? So this would be the probability X is less than or equal to 2. So this would be a CDF, binomial CDF. N is 8, P is 0.3, X is 2. I get 55.18%. What is the probability he hits the target at least 3 times? So at least 3 would be 3 or more. So this is greater than or equal to 3. So what I have to do is figure out the opposite of that, which would be 2 or less, and then subtract that from 1. All right, so I'm going to do 1 minus the previous answer that I just got, and I get 44.82%. All right, what is the probability that he hits the target less than 5 times? So the probability X is less than 5 is the same as the probability that X is less than or equal to 4. Okay, because remember your calculator does the less than or equal to for a CDF. So this would be a binomial CDF. N is 8, P is 0.3, X is 4. We get 94.2%. What is the probability that he hits the target more than 6 times? So greater than 6 is 1 minus the probability that X is less than or equal to 6. Okay, so I'm going to find 6 and below, subtract that from 1 to get the greater than 6. All right. How many times do we expect him to hit the target? So this is expected value, which is the mean. All right, so for a binomial mean, it's N times P. So 8 times 0.3, which would be 2.4. I expect him to hit the target 2.4 times. The standard deviation for a binomial is the square root of N times P times 1 minus P, which is the square root of 8 times 0.3 times 0.7. Also note that if you take statistics in the future, you may see 1 minus p written as q. Some other texts do that to simplify things a little bit. All right. Your turn. Go ahead and try this one. I will give you the answers in just a moment, but try it. See if you can solve it on your own. Use your calculator. All right. Hopefully you found that this one was binomial. N was 150. The probability of non-response was 55%. Probability of response was 45%. They did these all in terms of will respond. So using the 45%, you should have gotten these answers. And then for this part, here's your answers. All right, in this section, we're going to do like a little experiment. So I have a 35% chance of winning a game. Let X be the number of wins if I play 4 times. So create a probability distribution. All right, so how we can create a probability distribution without having to do all of the work is we can put this in our calculator. So this is a binomial distribution. All right, so it's a binomial distribution. So I'm going to go to Stat, Edit. I'm going to get rid of all the stuff that I have in here. And I'm going to put in my list 0 through 4. All right, so 0, 1, 2, 3, 4. And if I wanted to calculate all of the binomial probabilities of it happening on the 0, having 0 wins, 1 win, 2 wins, whatever, I'm going to go up to the top, highlight list 2, click enter, and I'm going to put my rule in, which I want it to do a binomial PDF. So I'm going to go to second bars, binomial PDF. Trials, I had 4 trials. The probability of success was 35%, so 0.35. And then the X value I want it to use is in list 1. So X values will be list 1, and I'm going to hit paste and enter, and it'll calculate all of those probabilities for me. All right, so that's what we get for our probabilities there. And then we can draw a rough sketch of a histogram, and we see that it's kind of slightly right skewed. I didn't do a very great job of my histogram, but it's okay. Describe the shape of the histogram. Okay, slightly skewed right. Try the sample with a size of 30. And what shape is this histogram? So instead of just doing 0 through 4, we could do 0 through 30 and then do the binomial. The only thing we need to change is n to be 30. And we can run that again, and you should see it becomes more normal as you increase the sample size. Okay, so what is considered a large enough n for the shape to look normal? Okay, so we have this condition that we're going to use throughout pretty much the rest of the year as we get into inference to check, can I use a normal distribution instead of having to do a binomial? So if n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10, so if I would expect to have at least 10 successes and at least 10 failures, then it passes, and then we can say that the distribution is approximately normal, and we can use a normal Cdf function instead. All right, so normal Cdf, remember, is where we put our lower bound, our upper bound, our mean, and our standard deviation. We use the mean and the standard deviation for the binomial, so that is a little bit different, right? If it's a binomial setting, you have to find the mean and the standard deviation using n times p and then the square root of n times p times 1 minus p. So it is said that 75% of people pay credit card bills on time. If we take a sample of 125 adults, what is the chance that over 80 of them will pay their bill on time this past month? All right, so I'm checking the conditions. N times p has to be greater than or equal to 10, which is also my expected value there. And then n times 1 minus p has to be greater than or equal to 10, which they both are. All right, so I can do a normal CDF. My lower bound would be 81. My upper bound would be 125. Because the highest it's going is to 125. It says over 80, so I'm going to go 81 and above. My mean is n times p, and my standard deviation is the square root of n times p times 1 minus p, and I get 0.9958. All right? And make sure you're labeling all of that. So assume 15% of adults jog regularly. We survey 1,000 adults. What is the probability that between 120 and 160 people in our sample jog? Okay, so again, I'm going to check those conditions. N times p has to be greater than or equal to 10. N times 1 minus p has to be greater than or equal to 10. They are. I'm going to find my mean and my standard deviation using the binomial rules, n times p for the mean, the square root of n times p times 1 minus p for the standard deviation. Then I can do a normal CDF, lower bound 120, upper bound 160, mean 150, standard deviation 11.29, and I get 80.82%. All right, go Seahawks.